Okay, so welcome again in our video series on refraction of light, and in this particular video we are going to answer a question that was given to me by a student that saw my video, and she was curious that if we take three medium instead of two, right? So let's say if we have one medium as vacuum, which is basically not a medium at all, but let's say we have vacuum, then we have glass, and then we have water, then what will happen, right? How will the light refract, and what are all the phenomenon that are gonna happen, right? So basically in this particular video we are going to answer that. Okay, so now let's see that what we are going to answer here. Basically we wanted to answer that if a light ray comes from glass and goes into the water, where will it go? Because we know that when it comes from vacuum and hits glass, it bends towards the normal, right? It bends towards the normal, right? And we also did a question regarding this in the last video. Please check that out if you haven't seen already. And we want to know, if it goes from glass to water, will it go towards the normal or will it move away from normal? And how do we measure that? How do we measure that, you might be asking? So we'll take the help of this R2 angle, right? We'll take the help of this R2 angle, and if this R2 angle comes out to be greater than I2, right? If it comes out to be greater than I2, then it has moved away from the normal, right? Because if it comes greater than I2, then it has moved away from normal. And if it comes lesser than I2, then it has moved towards the normal. And why is it important? Why is it important to see where it has moved? Because we want to know that what does happen to the light when it goes from glass to water, right? That's why we are seeing towards the angle, and we are trying to assess what the angle would be. Okay, so let's apply our laws. That no, not a law, basically not the laws, basically a particular law, Snell's law, that we have studied, and I mistakenly wrote it as SNAIL, but it actually is SNELL, right? So Snell's law. Okay, so basically what we are trying to do here, we are trying to see what this R2 will be. Okay, and we are trying to see that we are trying to basically prove that if light goes from, okay, so I'm writing it in a short form, goes from a rare medium to a dense medium, then it moved towards normal or away from normal, right? So towards / away. Okay, and if same thing goes from a dense medium to a rare medium, then will it go towards normal or will it go away from normal? Okay, so we have written our Snell's law here, and we have written n/1, right? The refractive index of the glass with respect to vacuum, which is nothing but its absolute refractive index, right? So basically we have written it v1 by v2 sin I1 by sin R1, right? And to find the refractive index of this particular phenomenon, that light going from glass towards water, we'll write N32. We'll write N32 to see if in this particular relative thing, water is denser or glass is denser, optically talking, right? So water has this, what we are trying to assess N32. Why do we are we trying to assess N32? Because it can give us R2, right? It's right in the formula. It can give us R2. Okay, and I have written this formula just on the basis of the diagram, and you can pause the video and look at them yourself. Okay, so to find N32, I can use a very neat trick. Okay, so I know what do I do? I know that N21 is v1 by v2, right? And by the same rule, N31 would be v1 by v3, right? So if I want to find N32, what I can do is I can just say that it is n31 divided by n21, right? n31 by n21. Why? Because if I take the values here and if I divide it, so if I write v1 by v3 divided by v1 by v2, so I will get v1 and v1 will go cancel out. Okay, I can write the whole calculation. v1 and v1 will cancel out and we will reach v2 by v3. So just by doing n31 by n21 I can find n32, and you can check because n32 will be defined in this way only, because n21 was defined v1 by v2, n31 was defined v1 by v3, so n32 will obviously be defined by v2 by v3, right? So we have got a really good relation here. We have got a really good relation here that we can just take the absolute refractive indices, of both the medium and we can just divide them to find n32, right? So let's just do that. We know that the absolute refractive index of glass comes out to be around 1.5, and the absolute refractive index of we are writing n31. So n31 is the refractive index of water with respect to vacuum, right? So absolute refractive index of water, so it comes around 1.33. You can look it up into the table, right? So 1.33 and n21 comes out to be around 1.5, right? And when you do this calculation, so it comes out to be 1.33 divided by 1.5 is around 0.88, right? Is around 0.88. Okay, now we want to find this particular R2, right? So for that, let's find R1 first, because we want to find I2, right? Because see, we have 0.88 in this equation. Look at this equation. We have this one value, right? This one value. Now we want to find this value, and we'll get this value by this relation, right? So to find I2, let's take the use of this equation. Now you might be saying, why do I use this equation? It doesn't even have I2 in it. You'll have to look deeper. You have studied angles in 9th class, right? In 9th grade you have studied your angles. Won't you say R1 and I2 are equal? If you have any doubt regarding that, you can reach out to me in the comments. And ask me that why are these angles equal? But you must know, because you have studied that in 9th grade. So R1 and I2 are equal. So if I am able to find R1, then I can find I2, and if I am able to find I2, then I will find R2 with our relation that we have written. Okay, so let's just by our mathematical sense, we can say R1 and I2 are equal. So let's find R1, right? So to find I2, we say that n21, which was nothing but glass's absolute refractive index, which we know it to be 1.5, and I1. Okay, so I1 is something that we control, right? I1 is something we control. We saw in our simulation that we can control our incident angle. We can control incident angle, and we can maneuver it. So let's take it to be a value that is much easier to work with. So let's say it's 30 degrees. Let's say it's like 30 degrees, right? Let's set I1 to be 30 degrees. Right? So for 30 degrees, we can write sine 30 degrees, and then we can write sine R1, right? We can find sine R1. So from here we can write sine R1 is equal to what is sine 30? You can look up in your textbook. It is 1 by 2, right? So 0.5 basically. It's 0.5. So it will be 0.5 divided by 1.5. Okay. So when we do this calculation, we find that it comes out to be 0.33. Right. Now to find R1, we do a particular operation which is basically is called sine inverse, right? Now I know that you are not even well versed with what sine actually is. Then how will we know what sine inverse is? So basically, just for now we can say that we took our sine here, and it converted into sine inverse. We can say that for now, but this is not what actually happens, but we can say it for right now. And in your calculators, in your mobile phones actually, you'll find, or any scientific calculator, you'll find a sine inverse button. So find a sine inverse button in your calculator and take the sine inverse of 0.33 with me. So when we take the sine inverse of 0.33, it comes out to be 19.26 or 27 if we take like an approximation. So 19.27 degree comes out to be the answer, and beware, when you use the calculator, you set it to the degree setting so that you'll get the right answer. Okay. Now I have R1. Now I have already written that R1 is equal to I2. Okay. Now I have I2. Now if I have I2, now I can easily calculate. Now I can easily calculate R2, right? Because I know N32. What was N32? N32 was 0.88. So N32 was 0.88, and I2 came out to be 19.27 degrees. So I can write 19.27 degrees, pardon my handwriting, and we can write sine R2, right? So from here we can find, take again sine 19.27, it will come out to be 0.3, because okay, you can calculate it. So sine R2 will come out to be, okay, let's move this a bit. Okay, so sine R2 will come out to be 0.33 divided by 0.88, which then we calculate 0.33 divided by 0.88, so it came out to be 0.375, and then let's take the sine inverse of 0.375. you can calculate it, you can see in your calculators or even in your mobile phone, there is the calculator, and you will find the inverse operations there also. Okay, so it comes out to be 22 degrees approximately. Now what did we say? We said that if R2 comes out to be greater than I2, then it moves away from normal, right? And that's exactly what we found out, that I2 came out to be approximately 19 degrees, right? It came out to be approximately 19 degrees, and this comes out to be approximately 22 degrees. So R2 is greater than I2, right? So it moves away from normal. And intuitively we know that, not even intuitively, if we look up the refractive index table, we know that glass has the refractive index of 1.5 and it has the refractive index of 1.33. So you will say that water is optically rarer than glass, right? So when this happens, so basically what is important here, what is important in this whole video, the concept that I want you to take from this video, aside from doing the whole lot of calculations, which is important for you. This is important because when we solve questions, we think, yeah, the theory was so easy, but the numerical is not happening. We are getting stuck in numerical. So I have shown a proper numerical to you so that you can do these questions on your own. Okay, so basically what I want you to take away from this video is that when light goes from rare medium to dense medium, it moves towards the normal. Okay, we can highlight it, right? And when it goes from a rare medium to a dense medium, when it goes from a dense medium to a rare medium, then it moves away from normal, as we saw, because this angle came out to be bigger than the incident angle, right? So I hope this is clear to you. If there's any doubt, then please let me know in the comments, and I'll see you in the next one. Thank you so much.